All right. Well, the three reservoirs homework is due on Wednesday of this week. And hopefully everybody got the email that I sent out on Friday afternoon with the updated information about that example from Friday. So the issue with that example was simply that the head at junction D was so close to the elevation in the middle reservoir that whether the flow is in or out of the reservoir, it was really close to the dividing line between whether the flow is in or out of the reservoir. So in the second iteration, when I started the goal seek, it wasn't able to find a solution because I was assuming that the flow was out of the reservoir when actually it was into the reservoir. So anyway, if you have any lingering questions about that example, the video that I posted, I edited out the incorrect information from that example and edited in the correct stuff. So there's the email that I sent, and then also the video has been corrected. So apologies for that. Go ahead.
Do you know why it was, like the solution from previous years wasn't the same or didn't work in that?
Well, I think that normally in previous years I would do the problem with the Darcy-Weisbach equation, which we did, and it solved fine. But when I did the Hazen-Williams equation in the past, I didn't use goal seek. I was just sort of keying it in by hand. And so I think it's because I was throwing the goal seek in rather than the by hand iteration. That's all I can figure. All right, so you've got till Wednesday for the three reservoirs. If you have any questions or problems as you're working on that, I've got office hours both from 11 till 12 and then also from 2 to 3 on Monday, Wednesday, and Friday. And then you're welcome to contact me outside of those hours, and I'll pick up on Teams calls if I'm available and respond to your emails when I'm able. Today we're going to talk about local losses, and I know that this is a topic we've touched on briefly in fluid mechanics, but we'll extend our discussion of that, and then we'll get some additional practice using the Moody diagram. I've printed out Moody diagrams for us to go through a couple of practice problems related to that. Are there any other questions before we continue? Maybe you saw this announcement slide as you were coming in about the FE review sessions. I know that most of you here probably aren't taking the FE exam in the immediate future, but I'd encourage you to consider attending these review sessions even if you're not taking the FE until next year, simply because it'll help you to retain some of these things that maybe you took a while back. For example, if you took transportation engineering a year ago and you're not going to be taking the FE for another year, then that's a lot of time to forget the material in between. So just a brief refresher would keep things in your mind until you're going to need it for the FE exam. So you can see the dates that are listed there, and I'll also send this out by email. The review sessions are from 4 to 6 on each of the days that are specified, and it's in 1205, which is just down the hall from here. Of course, the other announcement, just to remind you about, is the Division of Highways has their summer co-op program, and the application deadline for that is February 11th. So you've got just under 2 weeks to finalize that now. Okay, so local losses are reductions in energy that are caused by turbulence at a point. Remember that pressure drop through a pipe can occur even when it's a horizontal pipe because of the resistance to flow of the stationary surface exerting a shear stress to the water that moves past. And so that distributed loss, the friction loss, comprises the majority of the energy that's lost between points. But these local losses can also take a pretty healthy bite out of the available energy. And sometimes it's because of transition in the flow direction, like a bend. In other cases, it may be because of a change in diameter of the pipe that's flowing, and there's a variety of different ways to handle it. Usually, when you have a fitting that's provided by a commercial supplier, they'll also have the hydraulic characteristics of that. So if you're buying a commercial pipe bend, then the manufacturer of a valve or a bend has classified the energy loss and will give you the K value for that fitting. Because of the magnitude being smaller usually than friction losses, they're sometimes called minor losses. And so the overall head loss between 2 points is the sum of the friction losses and these local losses together. So when water flows from a reservoir into a pipe, that entrance is causing a reduction in energy because the water is going from stationary to moving, and it's having to enter the conduit, and so there are energy losses that can be attributed to pipe entrances, contractions, expansions, and we'll look at some of the specifics. There's K values that come out of the textbook. I think that these K values are from the fluid mechanics textbook. Oh, let's see, chapter 8. No, this might be our textbook, not the fluid mechanics textbook. But what you can see is that the larger K values come from a more abrupt transition in pipe sizes. And so this angle that it's measuring here kind of describes how gradually tapered the transition between diameters would be. So 180 degrees is just saying that you have no tapered transition whatsoever. That you have a large pipe that's feeding down into a small pipe, and so the water is experiencing some eddies and countercurrent flow that's causing turbulence right there at the inlet before it's reorganizing itself into the smaller diameter pipe. And so there's a larger K value for a situation like that than if it had been tapered and more gradual. And then the larger the difference in the pipe diameters, the bigger the K value as well. So this D1 to D2 ratio is simply saying that if the two pipes are approximately the same diameter, meaning that, for example here, the D2 is 90% of the diameter of D1, so it's only a little bit smaller, then the K value is pretty small because there's not as much energy loss than if it was a more extreme transition. So look at the 180 degree angle, meaning that sudden transition. If the downstream pipe is only 20% of the diameter of the upstream pipe, so this line would have the K value of 0.49. So that's nearly 5 times higher than the K value for the more gradual transition to a pipe that's 90% of the diameter. And then a similar thing is true also for the pipe expansions. We've got a variety of K values for globe valves versus gate valves. And part of the reason for that, if we look at a gate valve, the water flows through the gate valve when it's fully open. The K value would be really small, 0.15, because it's not causing much of a disruption to the flow that's going straight through the pipe when this gate's been pulled out of the way. It's catching maybe the edge of the gate as the water flows past. But in contrast to a globe valve where the water's having to go down, change direction, now it's flowing sideways when that valve is open, and it's changing direction again and it's flowing down, and the diameter of the flow through the globe is going to be smaller than the diameter of the flow of the pipe. You can kind of get a sense for why the K value would be so large, a K value of 10, in contrast to the relatively low reduction of energy that happens when there's the flow through the gate valve. Check valves are used to prevent water from flowing in an unintended direction. They use check valves in Huntington here. They have a problem in some parts of the city where sewage will go into people's basements. That like when the combined sewer is really full, the water would flow back and fill people's basements with sewage. And so they put check valves so that water can flow one direction through the pipes, meaning out to the street. But then when the sewer pipe is full and it would otherwise be going back towards people's basements and shower and bathroom, the check valve swings closed and prevents that sort of damage. So you can see that there's several different types of check valves. One of them is a ball type, where there's just a ball that is suspended and floats up when water's going one direction, but then the ball seals the valve when the water would try to go the other direction. And that would impose a K value of 70, which is really, that's basically 70, remember, is being multiplied by the velocity head. So whatever the velocity head is at a certain location, you multiply that by the K value, and then that will tell you the magnitude of energy loss in units of length. Water that's flowing from a reservoir into a pipe has an entrance coefficient of 0.5, but if the pipe extends into the reservoir rather than being mitered in at the edges, then the entrance coefficient is 1. If you have enough of a gradual bend and a transition, that K value can be knocked down to as low as 0.04. And if you have the angle of departure from the tank is anything other than just straight out at a 90-degree angle, then that can influence the K value as well. So this is just another look at the globe valve, and why its K value is going to be relatively high is because the diameter of the water flowing through this valve that's opened is going to be smaller than the inlet diameter of the pipe that's going into that valve. And so the majority of the energy loss is due to having to flow through a smaller orifice inside of the valve. Of course, there's also the change in direction that's causing a reduction in the energy that's flowing through it. You can see that a ball valve, which is, people like ball valves because of the convenience. You only have to turn it 90 degrees to go from fully open to fully closed. And the water is flowing through a segment of pipe that's embedded in a ball, and so there's a relatively smaller reduction in the flow energy through a ball valve than compared to a globe valve. This reference, this PDF data table, is a commercially available set of K values. You can see that the link was from Metro Pumps. And so Metro Pumps is a reseller of valves and pipes and fittings and pumps as well. But they have these K values for a variety of different pipe sizes, and so they make their own line of gate valves and globe valves. And so this is showing that which K value you would use depends on the diameter of the fitting as well. So it looks like they have a larger K value for the smaller diameter fittings. So for example, the globe valve that's only a 1/2 inch diameter has a K value of 9.2, but then when you get up to the larger 18 to 24 inch diameter pipe, there's less of an energy loss there. So every manufacturer of pipe fittings is going to have their own set of estimated or lab tested K values that they can provide. Okay, so let's just get some practice with this and use the Hazen-Williams equation as well. Water is flowing through a pipe network, and here at location A we know that the pressure of the water is 650 kilopascals. And then water is flowing through the pipe, and of course it's losing energy due to pipe friction. And we can use the Hazen-Williams equation to estimate the magnitude of that loss. So here the H sub F equation. And we know that whatever this pipe is made out of, it has a C value of 120. So we're going to calculate the pressure downstream at location B. And location B is higher up in elevation. And so there's going to in part be a pressure change just because of the difference in elevation, but then there's the friction loss, and then you can see that there's 3 fittings that the water's flowing through: a pipe bend, a globe valve, and another pipe bend. And since the pipe diameter is the same at all three locations, we can just add up the K values. If there was different pipe diameters, then you'd have to keep them separate because there'd be a different velocity where there's different pipe diameters. But here we can combine it together. And so ultimately you're solving for P2. So you're solving for the pressure downstream, solving for P2. And so let me pause there for a second, give you some time to calculate the energy loss. We know the flow velocity, so that makes things a little bit easier. It doesn't have to be calculated directly. Okay, the pressure at B is going to be quite a bit less because all of the factors that would impact the pressure are causing it to be reduced. There's the friction losses due to the pipe, there's the local losses due to these fittings, and then there's also the elevation difference. Where it's higher in elevation, it'll have less pressure because of that as well. So we need to first of all calculate the friction losses, then the local losses, and substitute that into the energy equation. And when we do that, for a 1,000 meter length pipe, Hazen-Williams equation predicts that there would be 43 meters of head loss due to the pipe friction. And then largely because of the globe valve that had a K value of 10, that's where the majority of the local losses are coming from, 8.48 meters of local losses. And so if we substitute them both into the energy equation, you can see here that what I'm saying is the head loss in the energy equation is these two terms, the friction loss term and the local loss term. Now, because the diameter of the pipe at both location 1 and location 2 is the same, then that means that the velocity at those two locations will be the same. So V1 equals V2, and therefore I've just dropped it out of the energy equation where I'm solving for P2. So you can see each of the substitutions here. There are 66.3 meters of head at location 1. And so there's the elevation term that's detracting some of that head. There's the friction loss term that's taking out some of that 66 meters of head, the local loss term. And so at location 2, there's only 21.3 kilopascals remaining. Most drinking water distribution networks would consider 240 kPa as an absolute minimum. And maybe during an emergency situation, like if there's a fire and there's really high draw from a pipe, you could have the pressure go down to 140 kilopascals, but this low of a pressure would be considered unacceptable. And so if we were doing this analysis and needed to make recommendations, then a good recommendation to look at would be, number one, could we switch out this globe valve maybe for a gate valve? Because a gate valve is going to have a much lower K value, and that would improve how much pressure is available at B. And then if that wasn't enough, if that switch from a globe valve to a gate valve didn't do the trick, then we'd probably need to increase the diameter of the pipe. And then that would reduce how much head loss there is and make more of it available at location B. But are there any questions on this example? That's for next time. There it is. All right. Well, so with the remaining time that we have today, we're going to look at a couple of problems with the Moody diagram. So let me hand this out. Okay, the handout I've just given you poses two different scenarios. The first is that water is flowing through a 45 millimeter diameter wrought iron pipe. And so the fact that it's wrought iron tells us the equivalent sand roughness is 0.045 millimeters. So it's a 45 millimeter diameter and a K-sub-S of 0.45. So that's convenient when we calculate the relative roughness. And then we also know the flow rate through the pipe. So that's the Q. And remember that in order to fix the Reynolds number, which is down here across the horizontal axis, we need to calculate the Reynolds number, and we can do so by the flow velocity times the diameter divided by the kinematic viscosity. So we will need to calculate Q from the flow rate divided by the area. So the flow rate in terms of cubic meters per second, and then you divide that by the area in terms of meters squared. Of course, area is pi d squared divided by 4. All right, so what I'd like you to do is just get some practice using the Moody diagram. So let's find out what's the applicable F value for both of these problems. The first is with some water that's flowing relatively slowly. The second problem is some kerosene that's flowing at a really high velocity. So we'll just get some practice working on two extremes of the Moody diagram. You can go ahead and collaborate with your classmates on this. Make sure that you're getting the right intercepts and curves and so on in the figure. But we'll take some time and then look at the solution together. If you've got the notes printed out, don't peek ahead, because I think the notes show the solution. But better that you try and practice this one on your own before looking at the solution. So in the first of the two, the water is flowing at a rate of 0.2827 liters per second. So that's, in other words, 2.827 times 10 to the minus fourth cubic meters per second. And you can see that I've calculated the area of the pipe. Here on the whiteboard, the area of the pipe is 1.59 times 10 to the minus third meters squared. So the flow velocity is 0.177 meters per second. And so we can calculate the Reynolds number from that by multiplying it by the pipe diameter of 0.045 meters, dividing by the kinematic viscosity, which is 1 times 10 to the minus 6. So the Reynolds number is 8,000. So 8 times 10 to the third. So here in the green line is the Reynolds number, 8 times 10 to the third. And then the red line represents the relative roughness. Since it's a 0.045 millimeter pipe and 45 millimeter diameter, the relative roughness is 0.001. So you'd follow the curve, find the point of intersection. So the F value for the first one should be 0.034. Now think about, what if the relative roughness had been 0.0015? Now I created this example so that it would follow this curve that's on the figure. But what if the relative roughness, you'd calculated it, was 0.0015? So if it's between the two, what you need to do is just stay between the lines the whole way. So if it was 0.0015, and we were intersecting with the 8,000 Reynolds number, then that would be this point. So it would be 0.035. See how what we were following was this guideline, which goes up, and we intersected the 8,000. But if it had been between this guideline that we followed and then the next one, which is 0.002, then that would take us further up on the left. So maybe the example should have been not right on one of the curves, but in between them, because that's the slightly trickier thing. All right, so let me pause for a second, give you some more time to do the calculations for the kerosene problem. It's flowing at a much larger flow rate. Even though the pipe diameter is bigger, it's still going to have a larger velocity. So this is going to be the other extreme. Here we're at the extreme low end of the Reynolds number range in the transition zone. We'll be well into the rough turbulent zone for the next one. All right, in the second example, we've got the K sub S value is much smaller here. Let's see. Oh no, it's larger, 0.10 millimeters. But it's a larger diameter pipe as well. So the relative roughness, the K sub S to D ratio is 0.0004. So that's going to put us on this curve. And then on the whiteboard, I've written the calculations for the Reynolds number. What you should get is that the Reynolds number is 1.5 times 10 to the 7th. Okay, so let's look at where that puts us on these points of intersection. 1.5 times 10 to the 7th is here on the extreme right edge of the Moody diagram. So 1.5 times 10 to the 7th, we're going up, looking for where does that intersect the 0.0004 curve, and then following it to the left. So it should be 0.016 is the friction factor. By the way, I don't know that kerosene would ever flow at 142 meters per second through this pipe. That's a pretty high velocity. But that's what it takes to get a Reynolds number that high. Okay, so where things are at is you've got this 3 reservoirs assignment on your plate. It's due Wednesday. As you're working on it, if you want to ask me any questions, feel free to contact me on Teams or stop by my office or send me an email. So I will see you on Wednesday.